Hello everyone and welcome to another episode of Nowhere Yudarris. This is your host Mahmoud Nowhere. So today we'll be speaking about acids and bases. We'll be breaking down what are acids, what are bases, what are Bronsted-Lowry bases and acids and Lewis acids, autoionization, pH, pK, all that stuff. Alright, so as always, don't forget to leave a comment with any topic you want me to cover. Like, share, and subscribe, and shall we get started? So Bronsted-Lowry acid is basically an acid that donates H plus. It donates its proton, and Bronsted-Lowry base is a base that accepts the proton. So we got here, for instance, we got the acid here with the proton, and then we got the base, in which the base will accept the the proton. Thus, when the acid donates its proton, it has a conjugate base, right? And then when the base accepts the proton, it has a conjugate acid. So, like I said, acid, when you have a Bronsted-Lowry acid and it donates, it has a conjugate base, and vice versa for the base. And then next we have the Lewis acid and Lewis base. Lewis acid is basically a electron acceptor. Alright, so kinda the opposite. If you think of it, kinda the opposite. Bronsted-Lowry donates, Bronsted-Lowry acid donates, Lewis acid accepts. And then we have the Lewis base, in which it actually donates instead of accepting. And when it donates, it forms a coordinate covalent bond. And that's what Lewis acid and Lewis bases are. And like later on, we're going to discuss coordination compounds that are basically mostly Lewis bases, in which they donate their electrons. Next, we have amphoteric molecules, and they act like acid or base, like water, amino acid, H2SO4, and hydroxides of metal, aluminum, zinc, Pb, and Cr. When water reacts with a base, it acts like an acid. So H2O plus a base, and then water has the conjugate base of it, because we said it donates its H, and then the base has its conjugate acid. Alright, so the H2O turns into OH. Alright, so that's the conjugate base of it, and basically the base turns into conjugate acid, and the vice versa. When the water reacts with the acid, it acts like a base, and then actually produces H3O. It kind of accepts the proton donated by the acid, and the acid turns into a conjugate base. So acids formed from oxy-ions are called oxyacids. So oxyacids are characterized by their ability to donate hydrogen ions, protons, basically to a solution, resulting in an increase in the concentration of the hydronium ion and a decrease in the pH. And now decreases the pH, increases the hydronium ions, H3O. When they end with ITE, it's OUS acids such as hypochlorite acid, hypochlorous acid, and when it ends with ATE, hypochloric acid or chlorate acid, turns into chloric acid. And then autoionization is the reaction of water with itself to form H3O plus OH minus. So H2O plus H2O gives you H3O plus OH minus. One of them is going to have a conjugate acid, and one of them is going to have a conjugate base. And Kw is the kind of represents the ion product constant of the water, and is the concentration of the hydronium ion and the hydroxide ion in the water. So H3O times OH is equal to 10 to the power of negative 14 at 25 Celsius or 298 Kelvin. This depends on the temperature, not pressure or volume, right? If H3 of the hydronium ion is more than 1 times negative 7, it's acidic, alright? If it's equal to that, it's neutral. If it's less than that, or 1 times 10 to the power of negative 7 is more than it, it's basic. And then this is depending on H3O, so hydronium divided hydroxide is equal to 10 to the power of negative 7. And then the pH plus POH is equal to 14. How do we calculate pH? So in order to calculate pH is equal to negative log H plus. So negative log plus the the proton concentration or the H plus concentration, then you can also have it as log times 1 divided by H. And the pOH is exactly the same thing, negative log, and then you have the OH molecule times the OH concentration equal log 1 divided OH. And let's say you get a question and it's like calculate the pH of 0.1 of the strong base in OH. So you got the base, the OH, and you need to calculate the acid. We already said that both of them added up is equal to 10 10 to the power of negative 14. So 10 to the power of negative 14 is equal to H plus, and then 0.1. You move this here, and then you have this is the H plus. Okay, so we have the H plus concentration. Now we need to plug it in into the pH. So negative log times 10 to the power of negative 14 divided 0.1 is equal to 13. But actually, yeah, you have the H plus, and then you want to calculate its pH, so it's that. So pK kind of describes the acid strength. So it's kind of the same like pH, but instead of H plus, it's actually Ka. So as pKa decreases, acid strength increases. Inversely proportional. So pK is inversely proportional with the acid strength. pH is also equal to 14 minus pOH, or 14 minus log OH. You can kind of play around with the equations. Strong acids such as HCl, HBr, HI, HNO3, HNSO4, they have no reverse reaction, they ionize 100%. Weak acids such as HF, NH4, HNO2, HNSO3, they ionize partially and they could have reverse reactions. So Ka is the acid dissociation constant, in which is the measure of the strength of the acid. Like we said, pKa is the calculation of the acid dissociation acid strength. Yeah, acid strength in the solution. So Ka is equal to H3O, the hydronium ion, times the acid divided by the conjugate of it. The smaller the Ka, the weaker the acid, and less it will dissociate. So here it's kind of different than pKa. pKa, the smaller the pKa, the stronger the acid. Here, if Ka is smaller, the weaker it is. Strong base such as OH, KOH, NaOH, BaOH, they're soluble 100% and they have electrolyte. Weak bases such as OH3 is insoluble and doesn't ionize well. In Kb is the same thing. The smaller the Kb, the weaker the base and less it will dissociate. So with Kb and Ka, the weaker they are, the worse they are. If Ka is less than 1, it's a weak acid. If Kb is less than 1, it's a weak base. So anything above 1, they're kind of like good acids or strong acids. And then next we have Henderson-Hasselbalch equation. So Henderson-Hasselbalch is basically to find the pH or the pOH using the pK or the pKb. By the way, Kb is like the base dissociation constant as well. And then pH is equal to pKa plus log acid divided its conjugate. Actually, sorry, it's the conjugate divided the acid, and then you got pOH is pKb plus log, and then it's the base divided, conjugate divided its base. And then conjugate acid is acid formed when the base gains a proton plus 1 hydrogen. And then conjugate base is formed when the acid loses a proton, 1 less hydrogen. If Ka is large, Kb is smaller. So that's inversely proportional. So if Ka is larger than Kb, that's usually the case. Strong acids produce weak conjugate bases and vice versa. Kind of weak acids produce strong conjugate bases. So it kind of works opposite. Strong acid and strong base is an example of it. They will dissociate 100% and they will produce salt and water. Strong acid plus weak base, they won't produce water because they are not hydroxides. right? So NH3 doesn't have an hydroxide, that's why it won't produce water. Weak acid plus strong base, it does have, what do you call it, an OH. It will produce water, not salt though. And weak acid plus weak base, it will produce neither salt, neither water. So strong acid plus strong base, the reaction produce salt and water because they neutralize each other. So A minus is the concentration of the conjugate base of the acid, and HA is the concentration of the acid, like I said. Just to make it clear in case you were confused, this is the conjugate base of the acid, and this is the acid. Alright, so this is going to be on the reactant side, this is on the product side, if it makes it easier for you. Next we have titrations. So titrations are not buffers, by the way. Buffers are basically weak acid and its conjugate base, or weak base and its conjugate acid. Titrations are performed, on the other hand, to determine the concentration of a known reactant. So they're performed by adding small volumes of a solution at known concentration, and at equivalence point, acid and bases are equal Na Va equal Na and B VB. And then strong acid and strong base titration. So equivalence point is at pH 7. So you start at the acid, let's say you have HCl, you start at like 2 pH for instance, and you keep adding slowly droplets of base. So the acid dominates, and as OH is added, it becomes less acidic, and at the end point it becomes more basic. It reaches a certain equivalence point, and then after equivalence point it becomes more basic. Next we have weak acid plus strong base titration. So with the weak acid, it starts a little bit higher than the strong acid. Let's say, I don't know, starts at 5 pH because it's a weak acid. So you keep adding OH until you reach the equivalence point. And the equivalence point could be a bit higher than 7, like 8 or 9. And it ends up as well, the end point is basic because it's a strong base. It produces a weak conjugate base and doesn't produce water, and it has a weaker conjugate acid. Strong acid plus weak base titration, so kind of the initial pH is basic with that. With the with the strong acid and weak base titration, the initial pH, no, sorry, I think, my bad, this is not supposed to be this, but it's actually supposed to be weak acid plus weak base. So with the weak acid and the weak base, what is happening is you start at an initial titration of like 10 to 12, and then you keep adding the acid until you produce until you kind of reach an equivalence point. You keep adding H plus H plus H plus, and the pH drops. And with the conjugate acid, the hydrogen ions are preferred more than the OH, produces a weak conjugate acid and a weaker conjugate base. Next we have polyvalent titration. Polyvalent titration is basically a type of titration used to determine concentration of sample that contains 2 or more substances. They react at multi-step reaction. So the titrant uses as a reactant more than one functional group of the analyte, which results in a more complex titration curve. So let's say Na2CO3 plus HCl. Alright, so little acid is added slowly by slowly. The initial starts at like a base. This is not really, you could kind of consider it kind of a strong base, or not weak and not really strong. And then you add slowly HCl, and CO3, the conjugate base, is more dominant. And then CO3, the second part, CO3 and HCO3 equal buffer region, and then CO3 is finally titrated. You kind of reach like almost a equivalence point, and then HCO3 is neutralized and is becoming more and more acidic. And that's it. Let me know if you have any questions, and have a blessed day.